Yeah, it's same kind of guy. We're in organic chemistry in this video. Of course, you know that in organic chemistry gives us basic knowledge for organic chemistry. Then when we talk about organic chemistry, of course, pharmaceutical chemistry, we are going to talk about quantum numbers. And here is the layout of what we are going to discuss. We are going to introduce our topic. In introduction, talk about this guy, the Max Planck, then quantum and quantum energy. We talk about the quantum numbers, which are these four quantum numbers: the principal quantum number, azimuth or angular momentum quantum number. Talk about the magnetic quantum number, electron spin quantum number. Then we go to pauli exclusion principle. Then we talk about, okay, how can we determine the possible numbers of electrons in an atom? That's what we are going to discuss. So let's go. Yes, Max Planck, this guy, Max Planck, he discovered that solids, when heated, there is energy in form of electromagnetic radiation. There is energy in form of electromagnetic radiations, and this energy has discrete values or discrete quantities. Has discrete quantities, and these quantities you can call them quanta. Quanta, this is the plural of quantum. When I talk about discrete quantities, meaning that these values, they are not continuous. If it is 1, it is 1. Then it can be 1, 2, 3, 4, like that. It can't be 1.2 or 1.5 or you say 2.6. You get? So they are discrete values. Meaning that, for example, we can use this illustration. This ball can be at this step, can be at this step, can be at this step up to this ground step, but it can't be in between here. It can't be in between. So that's what the discrete means. It has a discrete value. For example, if the atom is heated, its electrons will move from lower energy levels to higher energy levels. And the energy which is absorbed by the electrons when they are moving, they are in form of discrete quantities. And when the electrons are coming back from the higher energy levels to lower energy levels, there is energy. That energy released has discrete quantities because those electrons occupy a particular shell or orbitals in an atom. So that energy is discrete. When we talk about the quantum energy or quantum, what is quantum? Quantum means that this is the energy released or absorbed by an atom in form of electromagnetic radiation. And this energy can be used in these quantum numbers as we are going to see. So, for example, we have this diagram. An electron can be at a particular shell, can be at this shell 1, can be at this shell, this one or this one, but it can't be in the middle. Wherever it is, it has, the energy it has is in form of the discrete values, It's not continuous. So, quantum energy is given by this formula. This is the energy of the quantum energy. And this H is the Planck's constant, this guy. And it is 6.62 6 exponent negative 34. These are joules per second. They are joules per second. 6.626 exponent negative 34 joules per second. We are not going to that. So, but if you find this formula somewhere, of course, just know where it comes from. But we are not going to that. An illustration can be like this. We have an atom. This is the atom. When this atom is heated, it absorbs energy. When it absorbs energy, electrons will move from the lower energy levels to higher energy levels. For example, here, from here to higher energy levels, when the energy is absorbed. And when the electrons are coming back to lower energy levels, energy is released. That energy released is in form of electromagnetic radiation. When the electrons are coming back from higher energy levels to lower energy levels. And you can use this concept to describe our quantum numbers, as we are going to see. Yes, MK the guy. We are on quantum numbers now. As we describe the quantum and the quantum energy, the meaning, and how are they going to help us in quantum numbers. Here, in quantum numbers, these ones are used to describe the distribution or the state of electrons in an atom. So we use them to describe the distribution or the state of the states of the electrons in an atom. We have principal quantum numbers. For the principal quantum number, this one is denoted as n. So for the n, it tells us the shell or the main energy level, or you can call it the shell, where the atom is found, where the electron is found. So if n is equal to 1, so you can have 1, you can have 2, 3, like that. So if n equals to 1, means that the electron is in the shell 1 or the first energy level. When it is 2, means that electron is in the energy level 2. So the increase in energy level means that the farther away from the nucleus, or the farther from the nucleus. Means that it also tells us the distance away from the nucleus, this principal quantum number. Then we have azimuthal or angular momentum quantum number. For the angular momentum quantum number, let's rub this. For the azimuthal or angular momentum quantum number, this one tells us the shape of the orbitals, and its value is dependent on the principal quantum number. So if principal quantum number is equal to 1, the value of the azimuthal quantum number, it's either 0 to n minus 1, from 0 to n minus 1. So if n is equal to 1, means that for the azimuthal quantum number, it's 0, and n minus 1 means that it is only 0. So we have only 0 as the shape. So, and this 0 is for S orbital. If n is equal to 2, we shall have from 0. So we shall have 0. Then you go to n minus 1. So we shall have 1. Because if we say n minus 1, it is 2 minus 1, which is 1. So it has 0 and 1 if n is equal to 2. So mean that in the first shell, we have s orbitals here. If this is an atom, this is the first shell, we have s subshell. You have s subshell or s orbital. Then in n, if n is equal to 2, we have 0 and 1. This 0 is for s, this 1 is for p. So these are the two subshells. So it tells us the shape of the orbitals. And this one, if it is 0, means it's for s orbital. If it's 1, it's for p orbital. As you see here, this is the second shell. And in the second shell, we have the s orbital or the s subshell and the p subshell. This illustration just tells us, or it just gives us a picture in mind, like how the shells or the subshells are in energy levels. But it's not the exact, because electrons are not at the side like this, that this one is here, this one is here, this one is here. They are surrounding the nucleus. So if n is 2, this is the principal quantum number. If principal quantum number is 2, means that we are in shell 2. And in shell 2, we can only have s orbital and p orbital, or s subshell and p subshells. So if n is 3, so we can have 0, 1, and up to 2, because the maximum number is n minus 1. So n, which is our 3, minus 1, so maximum is 2. So at n is equal to 3, we can have, this one is for s, this is p, now this is d. These are the subshells. So what's the difference between shell, subshell, and orbitals? So this is the shell. These are shells. In the shells, we have subshells. So this is s, this is p. These are two subshells. And in the p subshell, we have orbitals. In p, we have 3 orbitals. These ones, they are the orbitals. It's the same here. This is our s, this is p, this is d. And in d, we have 5 orbitals. 1, 2, 3, 4, 5. Those are the 5 orbitals in the subshell. So this is the azimuth or the angular momentum quantum number. It tells us the shape. For the s, it is represented, it's denoted by 0. Then for p is 1, for d is 2. So it increases like that. These s, p, and d, they have some historical background. For example, okay, we have s, p, we have d, we have f, among others. These are just lines after electromagnetic radiation. They are the lines which were seen. This one, they were the sharp lines. Sharp lines. These ones, they are called principal because these lines were strong. Strong lines. These ones were diffuse. Then when it comes to F, they are called fundamental lines. Then from F, they just went to G, like alphabetically. F, G, H, like that. So nothing much there. But just know you have S, P, D, and F subshells. S subshell, they have this shape. This is their shape. When it comes to the p subshells, they have, or the p orbital, they have this shape. Then when it comes to the d, we shall see them here in magnetic quantum numbers. Let's see them because they have different structures. And when it comes to f, they are very complex. So we are going to see their shapes. This is for s, this is for p subshell. Let's go to magnetic quantum number. Then for magnetic quantum number, it's denoted by ML. We say that principal quantum number for it is denoted by N. Azimuthal or the angular momentum quantum number is denoted by L. Then for magnetic quantum number, it's M, L. Then we shall see electron spin. Also, it's denoted by MS. So, magnetic quantum number, this one tells us the orientation of an electron in space. And its value is dependent on the azimuthal or the angular momentum quantum number. So we use this formula, which is 2L plus 1 to get the ML value. Meaning that if, for example, if L is equal to 0, we can have the magnetic quantum number to be 2 times 0 plus 1. So we shall have 1. So we say that L is for S orbital. So for S, we have only one orientation in space. As we said, its shape is like this. So if this is our X, this is Y, and this is Z. For the orientation, if L is equal to 0, then for the ML, it is only one orientation. So it will be here, like this, in the middle. Then, for example, if L is equal to 1, we can have, using this formula, 2 times 1, then plus 1. So, mean that here it is 3. If the L value is 1, the ML value is 3. So we can have 3 orientations. And we say that if L is equal to 1, meaning that this is the P orbital. It's the P orbital. Meaning that in P, we can have 3 orientations. And we say that this is the shape for the P orbital. So we say that this is Y, this is X, and this is Z. So meaning that we can have orientation at X axis. If L is 1, this we can have 3 orientation, meaning that from -1, 0, and 1. So meaning that we have P at X, we have P at Y, and we have P at Z. So we can have this at X. Then we can have at Y, like this, orientation at Y. Then you can have at Z, like that. So those are the 3 orientation if L is 1, meaning that the P orbitals have these orientations, 3 orientations. Now, if L is equal to 2, meaning that you can have how many orientations? It is 2 times 2 plus 1. So these are the 5 orientations. Meaning that from -2, 1, -1, 0, 1, and 2. Those are the 5 orientations in space. And we say that if L is equal to 2, means that we are in the D orbital. We are in the D orbital. So orientation can be this, or that. Then in P orbital, this can be XY, you can have YZ, you can have XZ, then this is X squared minus Y squared, then for 2 it is Z squared. Those are the 5 orientations. So if this is our x, this is our y, and this is z. This is z, this is y, this is x. So all of them, it's the same thing. Z have y, we have x. So -2 xy means that we're in x and y orientation. So if this is x, this is y, we shall have orientation here in x and y. Here it is xy, and here. So we shall have orientation like that in between the xy. You see, this is yx. So we have that orientation. If you have yz, mean that it is in y and z. Y and z. So we shall have this yz. Even here it is yz, yz, and here it is yz. So mean that here shall have this. In yz. If you have xz, it's in between x and z. So this is our x and z, mean that you shall have this orientation here in xz. And here, this is xz. So we shall have those orientations. In x squared minus y squared, this is z, this is y, this is x. It will be in y itself like this, and in x like this. Then for z squared, it will be in z like this. It will be in z like that. Then surrounded by a ring. It will be surrounded by a ring. So if you find those shapes, don't get confused. This is z, this is y, this is x. For the z squared, it's like this. So this is the d orbital, or the d subshell. It has these orientations of the orbitals. This is xy, this is yz, this is xz, this is x squared minus y squared, this is z squared. So if you talk about the magnetic quantum number, it tells us the orientation of the electrons in space. And this is the formula. It's dependent on the angular momentum quantum number. Let's talk about the electron spin quantum number. Yes, for the electron spin quantum number, electron spin quantum number. This one is denoted by MS. This one describes the orientation of an electron in in the orbital. In an orbital, we have maximum of 2 electrons. And these ones cannot be pointed or oriented in the same direction. If one is oriented up or its spin is up, the other one will be down. So it's either positive a half or negative a half. This one means it is pointed upwards. This one means it is pointed downwards. But they cannot be pointed in the same direction, like this or like this. It's impossible. And this one determines whether the atom is paramagnetic or diamagnetic. For the paramagnetic, these atoms, they are attracted by magnet. Because they have net spin. These ones, they don't have net spin, so they lack net spin. And they are repelled. They are slightly repelled by the magnet. If an atom has a net spin, it can behave like a tiny magnet. For example, let's take a look of oxygen. Oxygen atom has atomic number of 8. That's its atomic number. So meaning that it is 2 to 6, right? Or it is 1s to 2s to 2p. This is 4 to p4. So when you look at this, the flow is like this from 1, then we come to 2, then 2p, from 2p you come to 3p. Then from 3s, from 3p you go to 4s. So that's our written. So from 1s we go to 2s, then from 2s we go to 2p. This is how the orbitals are filled. That's the order. Now, if this is the first shell, 1, means this is the second shell and it has 2 subshells, right? So in the first shell, we have 2 electrons, like this. In the second shell, we have 2 subshells. We have the S shell, the S subshell having 2 electrons. Then we have the P subshell. The P subshell is having 4 electrons, meaning that it has 1, 2, 3, and the fourth one is like this. So, meaning that it has these last 2 electrons which are not paired, yeah, and they have a net spin. They are all pointed upwards, meaning that this oxygen is paramagnetic. Oxygen is paramagnetic, can be attracted by the magnet because it has a net spin. These 2 electrons, they are not paired and they are pointed upwards. So it is paramagnetic. So this takes us to the Pauli's exclusion principle. Let's talk about it. When it comes to Pauli's exclusion principle, Pauli's exclusion principle, it states that no 2 electrons of an atom can have 4 quantum can have same 4 quantum numbers. No two electrons of an atom can have same 4 quantum numbers. For example, let's consider oxygen. Oxygen atom has atomic number of 8. So meaning that it is 1s2, 2s2, 2p4. This is first shell, this is second shell. Second shell has 2 sub-shells. So meaning that in the first shell we have this. In the second shell we have these. And here in the S subshell we have 2. In the third, in the P subshell we have these. Those are the electrons in those orbitals. Now let's consider this. These 2 electrons, we say that no 2 electrons of an atom can have same 4 quantum numbers. So we can consider these ones, but you can consider any and try. Let's consider these ones. For example, for principal quantum number, which is denoted by N, this is first shell. This is first shell, this is second shell. Mean that here N is equal to 2 for them, for these electrons, because this is the second shell, this is first shell. Now, azimuth or angular momentum quantum number, we say that if N is 2, the maximum number of L is equal to N minus 1. So, mean that we can have 0 and 1. But 0 means that we are in the S orbital. 1 means we are in the P orbital. So, since this is P orbital, this is S, this is also S. So, we are under P. Means that these electrons, they have L, or the azimuthal quantum number, as 1. Now, when it comes to the magnetic quantum number, which is denoted by ML, of these electrons, we say that it depends on this one. So if this one is 1, you can have orientation here as -1, 0, and 1. Okay. So this one shows that we are in the P orbital. So we are dealing with this subshell, or these orbitals. So orientation here can be -1, here is 0, here it is 1. So since they are in the same orbital, their orientation, both of them, is -1. So we are excluding these 2. Then when it comes to the electron spin, the ms, these electrons, one is pointed upwards, another one is pointed downwards. So one is positive a half and the other one is negative a half. So they have different electron spin. So they share all the 3, but they differ in the electron spin quantum number. Meaning that this principle is true. No 2 electrons of an atom can have same 4 quantum numbers. So how can we determine the possible number of electrons in an atom? To consider the possible number of electrons in an atom, this is the formula, which is 2n squared. Which atom? For example, if an atom has n, the principal quantum number, as 1, how many electrons can we expect that atom may have? So mean that it can have 2 times 1 squared. So if an atom is having 1 shell, mean that it can have a maximum of only 2 electrons. So if there is only 1 shell, maximum can be 2 electrons we can expect in that atom. So if n is equal to 2, what do we expect? Mean that it is 2 into bracket 2 squared. This is 4 times 2, so we expect this atom, this is 2 squared, which is 4 times 2, which is 8. We can expect 80 electrons at n is equal to 2. In the second shell, we expect 8 electrons maximum in this shell. So, mean that if this is the first shell, maximum we can have 2 electrons. In the second shell, maximum we can have 80 electrons. So mean that these 2 plus these 6, maximum is 8 in this subshell. I mean this shell. So for the third shell, if n is equal to 3, the maximum is 2 times 3 squared, which is 9. Mean that this is 18. Maximum, this shell can contain 18 electrons. You can try. In S, we have 2. Then on these 2, we add these 6. Those are 8. 8 plus these 1, 2, 3, 4, 5 plus 10. So these are 10 plus 8, mean that we can have 18 electrons in this shell maximum. Same for this, we use the same formula, which is 2n squared. Find the maximum number of electrons in a given shell. Let's do some examples. Yes, same kind of guy. Let's do these examples about quantum numbers. Let's do the solution. Question 1. What are the allowed values of ml when n is 4 and l is 1? ml means that they need the magnetic quantum number. If n is equal to 4, means that this is the shell, at shell, or the energy level 4. Then L, if L is equal to 1, means that we are dealing with the p orbital or p subshell. Means that here, this is 4p. And they want the magnetic quantum number. And we say that ml is equal to 2l plus 1. This is the formula we use. Means that they want the orientations, the possible orientations. They want the values. So, mean that if L is 1, we shall have 2 times 1 plus 1. So, answer is 3. So, we have 3 orientations. Mean that the values, if L is 1, we shall have -1, 0, and 1. Those are the 3 values of magnetic quantum number if n is 4 and L is 1. So this is what is wanted. Number 2, list the value of n, L, and ml for orbitals in the 4D subshell. So if we are dealing with a 4D subshell, now they want the n value. Meaning that 4D, our n is equal to 4. This 4 means that we are in the 4th energy level. And when you talk about the L depends on the n value. So L can have from 0 up to n minus 1. So it can be from 0 up to n minus 1, meaning that you can have 0, 1, 2, and 3. And we say that this 0 is for S, this is for P, this is for D, this is for F, as they continue. Meaning that if you are dealing with that D, for D subshell, mean that our value is 2. So our L is 2. Now, ML, we say that ML, it's also dependent on the L value. So if L is 2, our ML is equal to 2 times 2 plus 1. We use this formula here. Mean that our ML is 5. So this one, it tells us the orientations. Mean that we have 5 orientations in the D orbital. And it tells us in the D subshell. It also tells us the number of orbitals. It tells us the number of orbitals. In D, we have 5. The XY, the YZ, XZ, then X squared minus Y squared, and Z squared. So 1, 2, 3, 4, 5. That's the ML. Then question 3, write the 6 quantum numbers for an electron in 3p orbital. It is orbital, not the shell. So these are the orbitals of the 3p. We have 3. And you can have orientation at X, you can have orientation at Y, and orientation at Z. And these ones we can have in each orbital maximum of 2 electrons, either pointed upwards or pointed downwards. We can consider this electron first. If it is 3p orbital, means that the energy level, or N, is 3 for this one. Okay, the format is N, which is the principal quantum number, then the L, which is angular momentum quantum number, ML, and MS. That's the format. When you consider this one, our N, we said it is 3. Our L, the subshell, it is in the P subshell, so it is 1, because you said 0 is for S, 1 is for P, 2 is for D, as they continue. Then ML tells us the magnetic quantum number, or the orientation. If L is 1, if L is equal to 1, means that you can have 3 orientations according to this formula, 2L plus 1. So if L is 1, we can have 2 times 1 plus 1, which is 3. So you can have 3 orientations, meaning that you can have -1, 0, and 1. So if this one is this subshell, or this orbital, if it is -1, this is 0, this is 1. So if you consider this electron, mean that its ML is -1. Then MS is pointed upwards, so it is +0.5. Now, before this one, let's first consider only those ones which are pointed upwards. We on this one, same N, same L, but it's at 0. Its orientation is at 0, so it is 0. It's ML. Then S is also pointed upwards. Then you can have this one. It is at 3, 1, but it is at +1 here, and it is +0.5. So you see what changes? It is only the orientation, because they have the same electron spin and they have same magnetic, the same angular momentum quantum number, and same principal quantum number. What changes? It's only the magnetic quantum numbers. Now, we consider these ones which are pointed downwards, meaning that everything here will be -0.5 before you do anything for all of them. Now, if you come to this one, N value is the same. Here they are in energy level 3. Then L value is also 1, they under P subshell. Then ML orientation there, it is at, if you come to this one, it is at -1. Then orientation is, the spin is downwards, so it is -1/2. Now this one, N is 3 here. N is 3. We have 1. It's at 0 and it is -1/2. This last one, it's at 3, 1, and here it is orientation at 1 over the Z axis and -1/2. So this is -1, 0, 1, and they are all pointed downwards. Let's go to question 4. Question 4, write the maximum number of electrons in the principal level for N is equal to 3. Mean that this N is equal to 3. This is the shell at the energy level, when the energy level is 3. So you have an atom X. This is the first energy level, this is the second energy level, this is the third energy level. So we said our formula is 2n squared. So if n is equal to 3, means that this is 2 times 3 squared. So maximum number of electrons we expect in that energy level will be 18. That's the maximum number of electrons we expect to be in that subshell, in that energy level. Yes, it's MK the guy. Please don't forget to subscribe, like the videos, and share. Thanks so much.